Hey, hey! Hi! Wow, we're missing you guys. We're missing so many of you. We hope you're well. But wow, happy Friday to you. We're looking at mixtures and dilutions, but we've done these before. That's kind of a cool little pickup here. When we had chapter 1, we had all these little introductions to applications. You might remember we even had a mixture problem on our test where we just had to set up a differential equation. And I'm writing it out slightly differently right now, maybe to be a little more helpful. But let's review a few things. Let's let Q denote the amount in pounds of salt at any time t. The rate of change dq dt equals the rate at which salt enters the tank minus the rate at which the salt leaves the tank. Now, what we did two chapters ago, is we wrote rate in minus rate out. Q was salt, of course. And we had the rate that salt was coming into the tank minus the rate that it was coming out. Hopefully you remember that. But remember that we could deal with more complicated problems. Very well, you might have different rates of flowing water coming in as well as out. If the rate of flow in gallons per minute equal the amount going out, coming out in gallons per minute, then our volume of water remained the same. But sadly, what we could deal with is something a little bit more complicated. We could say, wow, what if things are changing ever so slightly? What if the rate of flow coming in is greater than the rate coming out? You'd imagine that water level, that saline level, would continue to rise. And that affects concentration of salt in the tank, of course. When we're talking about the concentration, we're talking about pounds of salt over how many gallons we have. So let's just get a few more things reviewed. We could say, let's say salt is coming in at E gallons per minute with B pounds per gallon. So if you think about that rate coming in, well, I'm going to write up here in the top right corner, we had E gallons per minute times B pounds per gallon. I'm even going to write the units out to really make it super obvious to see what's happening. Look, when you do that, when you multiply B pounds per gallon, you can see the gallons cancel out. You're left with pounds per minute. So we had gallons per minute, that's the rate of flow in, just of the liquid. But we have B pounds of salt per gallon, multiply them together, and that's how many pounds of salt come in a minute. Now, coming out gets to be more complicated. You see, coming out, we know that the flow coming out would be F gallons per minute. But guys, the concentration in terms of how many pounds of salt per gallon is really going to be tied into this sentence right here. The concentration of salt in pounds per gallon in the tank is Q, how many pounds of salt you have. V naught is your initial volume. It tells you how many gallons you have. But remember, E and F are relating to the flow coming into the tank as well as coming out. If E and F are equal, they cancel each other out. You have the same water level. But, look, E times T minus F of T, that can be changing. We could have our overall volume increase or decrease. So that's going to be the concentration of salt. That's in pounds per gallon. So let's revisit this differential equation. And we're going to talk about rate coming in and the rate coming out. The rate coming in, we just said up above, it's E times B. We did that in the top right corner. That's pounds of salt per minute. But when we address what is coming out, the rate coming out in terms of pounds of salt, you could say, well, yeah, we've got F gallons per minute, but we're going to multiply that to Q all over V naught plus ET minus FT. Why? Well, remember what F was measured in. F, as we said, was measured in gallons per minute. When you're looking at Q all over V naught plus ET minus FT, we just said that was pounds per gallon. And once again, look, the gallons cancel out. That's how we have pounds of salt per minute. So this is our differential equation right here. And once again, you might wonder, answering the big question, does this appear to be separable, knowing that E and B are constants? Would this appear to be separable right now? No way. You can say, I'm going to divide both sides by that right-hand side. And guys, sadly, you do have a Q in there, but you also have a T. You can't separate them. But just like this last homework problem that we did, we might wonder if we could maybe reposition some things. And we will. We're going to say, my goodness, add the rate going out. And you'd get F all over V naught plus ET minus FT times Q equals E times B. Now I hope that looks to be a little bit more familiar. What type of differential equation would that be? Linear, absolutely. So we can find an integrating factor and we can move on from there. Again, I think maybe the trickiest part is dealing with that rate coming out, because it's not just the flow of the liquid coming out. You have to throw in the concentration of salt. And if you really think about it, you only have so many pounds of salt in there, and if that amount of water in the tank is changing, then that concentration of salt per gallon is changing. And that's how you have to set that up. Okay, well, if we have this information, and this is hopefully a not so bad of a setup, maybe, just maybe, with this information, we could solve this example. And this is where we're going, guys. We're going to do more than just set up a differential equation now. We're actually going to solve it. And it says, suppose that E is 3 gallons per minute. So water coming into the tank is 3 gallons per minute. And the flow coming in is 5 pounds of salt per gallon. What's coming out? Well, you've got 2 gallons per minute coming out. Now let me ask you this, just from a plain common sense approach. If you've got 3 gallons per minute coming in, you've got 2 gallons per minute coming out, over time, would you expect that saline water level would be rising or falling? What do you think? Rising. There's more water coming in, isn't there? There's more water coming in. So that's why we need that funny looking fraction right there, because look, normally you just say Q is the amount of salt divided by the volume. Well, your volume is changing. The volume is changing, and that's what we've got. So look, we can use this setup to help us out. We could say the differential equation we're going to have is dq dt. And what's coming out? Well, we've got 2 gallons per minute coming out. We're going to start with 10 gallons as an initial volume. We've got ET, so we're going to say there's 3T minus 2 gallons per minute. That's your F. That's 2T. And we'll multiply that times Q. And we'll say E times B. Well, E times B, that's 3 times 5. Well, do you know what? The setup is virtually done. We're going to have to go ahead and find an integrating factor. Let's see, 3t minus 2t is just, thankfully, 1t. And over here we've got 15. By the way, forgive me, I forgot to mention this other part of the problem. We are beginning A A is always the amount of salt that we start with. I think I might have rushed through that part of the problem. A, it starts off, the initial volume is V naught. A is the pounds of salt when we have V naught. So A is your beginning amount of salt. It's what Q is equal to when T is equal to 0. Okay, so we're looking at this. I hope we can see that we need an integrating factor. And let's see what we're going to have to find here. Here's our integrating factor. We'll have E, and then we're going to say integral of 2 over 10 plus t with respect to t. And oh my goodness, look at this thing. Well, we could pull out a 2. Hey, what's the antiderivative of just 1 all over 10 plus t? What do you think that is? ln of 10 plus t. How about that? And then kids will be like, well, wait a minute, hold on a second. How about I raise that up here to 10 plus t squared? And guess what our integrating factor is? 10 plus t quantity squared. Wow. Well, you know what to do with that. We're going to multiply 10 plus t quantity squared everywhere. Everywhere. That gets multiplied to every part of the problem. So I'm going to get 10 plus t quantity squared times dq dt. Hey, when I multiply 10 plus t quantity squared to 2 over 10 plus t, what are we left with? A 2 and then a 10 plus t. Look at that. One of the 10 plus t's cancel out. And look at that. Okay, wow, we're getting there. Left-hand side, you know how integrating factors always are working. This is really a product rule. What product rule? What function times what? What do you think? 10 plus t quantity squared times q. Oh, look at that. That's not so bad. And then we're going to integrate this, both sides, with respect to t. And my goodness, our left-hand side, we get 10 plus t quantity squared times q. Ooh, you know what? Let's get some calculus practice here. Sometimes kids will say, I'm going to do a u substitution. Hope you can even do that in your head. Imagine it was 15u squared. We'd bump that up to, what, the third power, right? And then we'd have to divide by 3. So what are we going to have then? 5, u to the third. And what was our u again? It was 10 plus t. And we've got that. Now double check that you're right. If you've just taken your antiderivative correctly, take a derivative right now. Are we right? Yeah, take the derivative, you're good. Oh, don't forget this pesky little constant. Doesn't go away. Wow, we are so close to solving for q. So close to solving for q. Guess what we got to do? Divide by 10 plus t, quantity squared. Even the constant. Even the constant gets that. All right, so we have q is equal to 5 times 10 plus t plus c all over 10 plus t quantity squared. But we said that our initial amount of salt, how many pounds was it? It was 3 pounds of salt. Sometimes kids are like, what does that mean? It means q is equal to 3 when t equals 0. Okay, q is equal to 3 when t is equal to 0. So let's plug that in. 3. Here's 5, and here's 10 plus 0. That's just a 10, of course. We can leave that. And then we've got c all over. Well, if t is equal to 0, we get 10 squared. Wow, that's just 100. This is 3, and this is 50. Subtract 50, you get negative 47. And surprise, surprise, you get a rather large looking constant. You get that. But my goodness, here we go. If you want to distribute a 5